Thank you very much, and a big thanks to the organizers for giving me this opportunity to speak about scale-free percolation. Also a big thanks to the organizers for arranging a solar eclipse right before my talk. That was actually quite lovely. Unfortunately, not much of it was visible. All right, so I'll be talking about scale-free percolation. This is joint work with Mia Daven, who is in the audience, sitting in the one but last row there. So should you ask me any questions and you find my answer not satisfactory, do go and try her. Maybe she's better at answering your question. And this is also joint work with Gerard Hooghiemstra, who has arguably the most difficult Dutch name. So if you want to try on difficult Dutch names, you should try his. All right. So it's not obvious what scale-free percolation is. So I'll have to explain that to you. But before I do that, I would like to start by giving a little bit of motivation as to why we would be interested in a model like scale-free percolation. And this has all to do with complex networks. So if my handwriting is not visible, do notify me. I'll try to write nicely. This is the first time I'm doing this talk on the blackboard. I think it's lovely to have such beautiful blackboards. One should use those. All right, so complex networks. There has been a lot of investigations, particularly empirical investigations of different networks. And here you can think about the internet, social networks, the World Wide Web, citation networks, the brain. There are lots of examples of real-world networks that people are trying to get information out of. And you know, these complex networks have various origins. They come from all sorts of fields, ranging from biology to sociology to computer science, etc. And one of the remarkable features is that many of these complex networks actually share some features. I mean, that they're in certain aspects different is what one would believe immediately. But actually, they're also similar in some ways. And the two most commonly investigated common features are that many of these networks are scale-free. And that's the scale-free that the title refers to. And it's not a very well-defined notion what it is to be scale-free. One way of visualizing a network that is scale-free is that it has a huge amount of variability in the amount of connections that the entities of the network make. So the majority of the network elements have rather limited number of connections, maybe between 1 and 10. But there are these occasional elements that have tons of connections. It could be 1,000, it could even be 10,000. Right, so we're amongst mathematicians, so one example is the collaboration graph between mathematicians, and the vertices of this graph are us. And you connect two mathematicians with one another when they've collaborated on a paper. Yeah? So this is actually data that you could download from MathSciNet. And if you do this, what you will see lots of mathematicians that have 0 collaborators, or 1 or 2. And actually, a lot of the papers in MathSciNet are written by authors who may have been master students or so. So actually, they don't have a lot of collaborators. But you have these occasional people who have tons of them. And of course, the best known example is Erdős, who has over 500 collaborators. So he's worked on papers, written papers with more than 500 people. And that really is a lot. And in a certain sense, you could say that this is what scale-free is all about. There is no typical scale, and it's a bit like the income of people. And in the Netherlands, the average or the median income is about 20,000 euros. But there are lots of people who earn twice that much, or 4 times as much, or 10 times as much, or 100 times as much, right? So it's a bit difficult to think about 20,000 as being sort of the typical income in the Netherlands. That's not true. That's far from true. And that's what scale-free refers to. And it's the same with the collaboration graph amongst mathematicians. The people who earn a lot probably play an important role in society. Right? Erdős had lots of collaborators. Well, he was a very important mathematician. So often in these scale-free networks, the people who have the most, or the entities that have the most connections, also play a very important role in the network's functionality. So that's interesting. At least that's what I find. So how to define this? Well, one way of doing that is by looking at the empirical distribution of the degrees. And actually it's better to look at the tails of this. I'll write that like that. So the n refers to the size of the network, and the larger than k refers to the fact that I'm interested in those entities that have more than k degrees. So what would this be? This is just the proportion of vertices in my network, which I can just think of as being the collection 1 up to n, which I'll denote like that. And then I'm looking at the indicator that the degree of the vertex that I'm looking at is at least k. Now, as it turns out, in many of the networks that are empirically investigated, this is a relatively nice distribution. So that means that many of these networks are actually relatively sparse. It's not true that, let's say, the average degree tends to infinity as the graph becomes bigger. That could, of course, also be the case. But it turns out not to be the case. Now, scale freeness is related to somehow the asymptotic properties of these tail degrees. And it's basically saying that this is roughly like an inverse power of k, where gamma is some value which is typically larger than 1. So that's what the empirical data suggests. And one way of visualizing this is in what they call a log-log plot. So you plot the log of this versus the log of k. And if a relation like this would be perfectly true, then this log-log plot would just show a straight line with slope minus gamma. Now, of course, in the real world, if you really plot this, you are going to get something which is a bit rougher, but you can, in many cases, see something like a straight line there. Now, of course, there's a lot of fuss about this because, you know, if you view this as a statistical problem, it's actually notoriously difficult to estimate this gamma, even if you have IID data. So, okay, but at the sort of at the higher level, this is what you can think of as being scale-free. Now, in the empirical work, what we often see is a gamma that is in between 1 and 2. And that's interesting, because gamma larger than 1 means that the mean is finite. That's because these tails are summable, and therefore the average is finite. But when gamma is smaller than 2, the variance is infinite. So this is typically what you expect to happen in sort of heavy-tailed random variables. Finite mean, infinite variance. All right, so that's one aspect of networks that we often see. Is this clear? All right. The second is that many of these networks are small worlds. And again, this is a very loosely defined notion. It somehow refers to the fact that typical distances in the network are much smaller than the network. So we're thinking about networks that could consist of 100,000s of elements, yet if I happen to pick two vertices uniformly at random, the graph distance between those would be maybe 5, 6, 7, maybe 10, but not a lot larger. So that really is very small compared to the network size. And that's of course not what you see when you were to pick a square in Z2 and pick two vertices uniformly at random. Because if I want there to be n vertices, then I have to take the square of width, square root of n, and then two typically chosen vertices are going to be square root of n apart. That's actually quite large. The square root of 1,000,000 is still sizable, much larger than 10. So this is not true in many of these empirical networks. So this can be phrased as typical distances, graph distances, or intrinsic distances are small. And in all of the modeling that we've been doing, what this small means depends a bit on the kind of model that you're investigating, but the thing that you could have in mind is graph distances that grow at most logarithmically in the size of the network. And if you were to have a network that has bounded degree, then you also know that the graph distances should grow at least like log n. So log n really is quite small. Now, and in some cases it can even be smaller than that. Something like log of n, which is very small. And that's sometimes called ultra small distances. All right, so that's the two features of complex networks that we see in many empirical networks. So that, of course, immediately raises the question, how to model such networks. And you can try various approaches. And the approach that is taken mostly is to model these networks using random graphs. We haven't heard that much yet about random graphs, and I will not say much about that either because I'm going to go to percolation. But what you should bear in mind is that you have a network of a fixed size, 100,000, and you have some way of connecting the vertices between one another, and the rule is intrinsically probabilistic. So the simplest example is the Erdős-Rényi random graph. So in the Erdős-Rényi random graph, you draw an edge between any pair of vertices completely independently from one another, and also in an IID way, with a probability that is the same for every pair, and often it's written in the form lambda over n, where n denotes the size. And if you choose it this way, the average degree will be lambda, and in most of our settings the average degree is bounded, so this is the appropriate setting. Of course, this is completely homogeneous. And therefore, it's not at all scale-free. Because in order to be scale-free, you need to have elements that are quite different from other elements. And this is not going to happen here. Here, the empirical degree distribution will converge to a Poisson law, because you can just compute what the degree of a vertex is. That's going to be binomial with parameters n minus 1 and p, which is lambda over n. That's very close to a Poisson. Now, Poisson has very thin tails, not thick tails. It's not heavy-tailed. So this is not scale-free. However, it's not that difficult to adapt the model in a certain way in order for it to become scale-free. So one way of doing that is giving the vertices a weight, which is IID, and has sufficiently thick tails, and then you connect the vertices, when you know the weights, conditionally on the weights, independently, but with probabilities that depend on the weights in a certain way. And that creates inhomogeneity, and if you choose your inhomogeneity in the right way, you can have a network that becomes scale-free. So one way of doing that is what I often call the Norros-Rayleigh model, or it's sometimes called the Poissonian random graph. And in this setting, you choose IID weights, and the edge between I and j is there with probability 1 minus e to the power minus, let's say, lambda wi wj over n. So if you were to take all of these to be the right constant, then you retrieve the Erdős-Rényi random graph, and you indeed see that all the vertices are the same. If they vary a lot, then you're going to get rather different edge probabilities, and therefore also rather different degree properties in the graph. And it turns out that if you want this model to be scale-free, you have to start with these edge weights to be, or the vertex weights to be IID as well, and then the power law will be the same. Okay. All right. So that's one way how you could model it. But in these models, what you typically see is that the random graph is very much like a tree. There are some cycles, but they're very rare. Now, in most of the real-world networks, this is not the case. You have a lot of clustering. Right? Think about a social network. If two of my friends, I have two friends, they're very likely to know one another as well. That will create a small triangle. So all of you have lots of triangles in your social network. They're not going to be there in a model like this. So in that respect, this is not a good model. So the question is, how can one create a model that has better, let's say, clustering properties? So this is often called the clustering coefficient, the proportion of wedges that are actually triangles. So that's one feature that is not quite appropriate in this model. Another feature is that, in most of the real-world networks, the entities are located somewhere in space. They have a geometric component. And these random graphs are often completely non-geometric. You would like to take that geometry into account, because people who live closer to one another are more likely to know one another than people who live very far away, despite the fact that we all know people who live very far away. Right? So this is this balance that we're trying to strike here. So the bad aspect about this model is that it has very low clustering and it's non-geometric. Now, of course, we do know lots of models that are geometric and that are random graphs. So that's percolation. Now, in percolation, the setting is often quite different. We're on an infinite lattice. That immediately means that phase transitions are well defined, are completely unique, etc. That's actually quite nice. So here the vertex set is ZD. And then we connect two vertices with a certain probability that depends on the edge between them. So one well-known example is what is called long-range percolation. And in long-range percolation, all the edges are there independently of one another with a probability that depends on x, y. And in this case, you get something like. So lambda can be thought of as the percolation parameter, and alpha is a certain exponent. And somehow this measures the geometry of the model. This is also what David Aldous mentioned in his talk. To include geometry in your models, and long-range geometry. Now, percolation is a beautiful model, and one should certainly investigate it. But for real complex networks, it's not an appropriate model either. Now, why is that? Well, the nice thing about this is that you can explicitly write out what the degree of a vertex is. That's just the sum of indicators. That's the sum over x. And these indicators, they're independent, and they have edge probabilities that are like this. Right? Now, if you have a sum of independent random variables, or independent indicators, we know that, well, the expectation can be very easily computed. That's just the sum over x, p naught x. But what is worse is that you can also compute the variance of the degree, and that's going to be the sum over x. The variance of an indicator, which is p0x, 1 minus p0x. So in particular, this is always smaller than the expectation. So if you look at my modeling, in the empirical work, we see that gamma is often in between 1 and 2, and that means that you have infinite variance, but finite mean. That's not possible because the variance is always smaller than the mean. Right? So percolation cannot be scale-free. It has nice clustering properties, and it is pretty long range, which makes it nice, but it's not scale-free. So the question is, how can we build a model that has both these features in it? So on the one hand, it's a spatial model. It has a long range properties. It has nice clustering. On the other hand, we're relatively flexible in choosing the degree distributions, and in particular, we can make the degree distribution such that it could have infinite variance while it has finite mean. Now, the way to do that is by combining these two features. This one and that one. So you could call that percolation in a random environment. So what is my model? As in the Norris-Rijtu model, I'm going to associate weights to the vertices, and they're IID. Okay? And then conditionally on the weights, the edges are present independently with edge probability Pxy, which is 1 minus e to the power minus lambda wx wy over x minus y to the power alpha. So that really is smack in the middle between this and that, right? So it's spatial, it has nice clustering properties, and now what I'll try to argue is that this model is also scale-free, and that's then where the name scale-free percolation comes from. Any questions so far? All right. So, what are we interested in? Well, it's the kind of properties that we've seen over there. So we wish to study degrees, we wish to study distances, but of course, I mean, we also are interested in the percolative properties because it's also a percolation model. And percolation properties are rather interesting. And in a certain sense, this should be done before you can investigate distances. Because if you don't have an infinite component, how do you define the distances? I mean, basically all distances are infinite. So we better be in the percolative regime. All right. So I'll actually discuss the properties in that order, starting with the degrees.
Let me ask you
Yes.
a question.
Yes.
If you take critical calculation, standard critical calculation.
Yes.
So in physics, one would say, well, it's you know, they have power laws everywhere. There are power laws everywhere, so you would say.
Yeah, but not in the degrees.
Okay, not in the degrees.
Yeah, so you are quite right. There are power laws, but more in terms of the cluster size. I mean, the degrees are just a binomial. They're actually bounded even. So that's a big difference. Good question. All right, so let's look at the degrees. Now I'll limit myself to a slightly to a scale-free setting, in the sense that I will be assuming that my IID weights are scale-free themselves. And I'll just assume that this is a pure power law, let's say for W larger than 1. Now why is this? Well, if all the weights, if the weights would be bounded, then it's not very difficult to see that also this cannot have infinite variance. Okay? So that's what I'm going to be assuming. And then, of course, the question arises how the degree properties depend on the parameters in the model, and what parameters do I have? Well, for the degree structure, the lambda will not be that relevant, but the alpha will. And of course the dimension of the graph, so alpha, dimension of the graph, and then also this power law exponent. So these are my three characteristic parameters. And it turns out that the degree structure is really characterized by that. So theorem 1. It is possible that the degrees are all infinity. Well, at least those degrees that have a positive weight. Because if you have a zero weight, then clearly your degree is going to be zero. When either alpha is less than or equal to d, or gamma, which is alpha times tau minus 1 over d, is less than or equal to 1. Okay? So this is the setting where every vertex, well, at least every vertex that has a positive weight, will have infinite degree. That may not be the most interesting setting. And the second theorem says, for power law weights, when this gamma parameter is larger than 1, the probability that d naught is larger than s is approximately s to the power minus gamma. Of course, there's a constant here, which I'm ignoring. So this says that in this setting, when you have power law weights, you also have power law degrees. And because I see what gamma is here, I know that I have to take gamma in between 1 and 2 in order for this model to have infinite variance. But if gamma is larger than 1, the mean of the degrees will be finite. So in this setting, you can have a situation that you're scale free. Okay? All right. So because you have this scale free behavior, we call it scale free percolation. All right. So I want to say something about the proof. This proof is not very complicated. It's very much similar to what occurs in the long-range percolation setting, which corresponds to this. In the long-range percolation setting, if alpha is less than or equal to d, the degrees are all infinite, with probability 1, or almost surely. So I will not say much about that. But let me say something about this. This may be more interesting. Okay, so proof theorem 2.
Let me ask you a question, Mike.
Yep.
Suppose you go back to your model of mathematicians.
What? Yes?
For the mathematicians, there are connectivities. What would be the dimension?
If you embed the people on the sphere, then it would be two-dimensional.
That's not really relevant. Or maybe infinite dimension?
It's not clear. You may ask the question whether geometry plays any role. I think it does. I'm more likely to work with people in Eindhoven than I'm likely to work with people in... Still. So I would guess that the geometry really does play a role. Okay. We crucially use the asymptotics of a certain peculiar sum, and it's this sum. And this is alike the edge probabilities that you see over here. It's just that we take x to be equal to 0, and we take a to be very large. Then this turns out to be roughly the same as some constant, which depends on d and on alpha, a to the power d over alpha. Well, actually it's equal to this, 1 plus small 1. That's not a very difficult computation. Basically what you're saying is that if y is quite small, then this is very much like 1. If y is extremely large, this is basically 0. What is the truncation value? Well, when this is of the order 1. And how many vertices are there for which this is of the order 1? Precisely that many. So that's the whole idea behind this proof. Now, of course, it may not be obvious that this is useful. So what are we going to do now? Well, let's first look at the expected degree. But I'm not going to look at the expected degree. I'm going to look at the conditional expectation, given that I know what the weight of the vertex is. Okay? Well, what is this? Well, that's of course the sum over y unequal to 0. And then we get 1 minus the expectation e to the power minus wy over y to the power alpha. That's just an equality. Now bear in mind that of course two edges are never independent. So if I look at the root, look at the origin, then the edges coming out of it will not be independent. That's because they all have this W0 in them. But if I condition on W0, they will be independent. So if I condition on W0, I'm dealing with a sum of independent random variables. Now we know a lot about sums of independent random variables. Particularly they get very concentrated. And that's what this proof uses. So now I'm looking at the mean, and because I'm dealing with a sum of independent random variables, if this mean is very big, then the random variable is going to be highly concentrated. So what is this mean? Well, I'm just going to bluntly substitute in this, because I'm thinking about W as being very large. The only way to have a very large degree is to have a very large weight. And then this is going to be roughly the sum over y unequal to 0, v d alpha, expectation of, well, the variable, which is this, raised to the power d over alpha. Now, as it turns out, this expectation of the w's will actually be finite. So then, oh, I've already done the sum over y. That expectation will be finite, so this is roughly a constant times w to the power d over alpha. And so what we see is that if I want to have an expected degree which is quite large, I better choose my little w to be quite large. But if my little w is quite large, I'm dealing with a sum of independent indicators with a very high mean. Therefore, it's very highly concentrated. So this is suggesting that if I want my degree to be quite large, like I have here, S is quite large, then I better have that this is quite large. So this should roughly be the probability that its expectation, which is a constant times W naught divided by times to the power d over alpha, is larger than S. But that I know, because that's precisely this. So that's going to give me S to the power minus alpha over d, which is the value here, times minus 1 times a constant. Okay? And that by definition is just a constant times S to the power minus gamma, because that's precisely gamma. And there we go. This is not very difficult. Any questions about this? All right. Now, of course, we also have a percolation model, and that immediately raises the question, what are the percolative properties? So if I define the percolation parameter here, which is lambda, then you would believe that if my lambda is extremely large, I have many edges, and therefore I should have an infinite component, whereas if lambda is extremely small, my edge probabilities are quite small, so you're not likely to have an infinite component. So the question is this true? So let me start by defining the relevant percolation properties. So, 3. Percolation. So from now on I will be assuming that gamma is larger than 1. Why? Well, if gamma is less than or equal to 1, actually the degree of every vertex is infinite, so there has to be an infinite component. So the percolation question is not very interesting. Okay? So I'll be assuming that gamma is larger than 1. And then we write that x is connected to y when there exists a path, an occupied path of edges connecting x to y. The usual percolation definition. And then I will define the cluster over vertex x to be the set of all y for which x is connected to y. Yeah? And then percolation is all about, is there a positive probability for this object to be infinite, or will it always be finite? Okay? So, for that, let me define theta of lambda, which is the percolation function, and that's the probability that this cluster, it's translation invariant, so I might as well take the origin, this cluster is infinity, has infinite size. Okay? Now, of course, this probability could be 0, it could be 1, it could be anything, but the question is this positive? So the critical value would correspond to lambda c, which is the inf over all lambda for which theta of lambda is strictly positive. Okay? And the question is this lambda c finite? Is it infinite? What are the properties? Is it positive? I have 3 theorems about this, and the first one deals with finiteness. Okay? And here I'll be assuming that the dimension is greater than or equal to 2. Those of you who know something about percolation know that dimension 1 is rather special for percolation. That's the same thing here. There are actually settings where you can have percolation in dimension 1, but it's a bit more messy. Okay? And then the statement says lambda c is finite. Okay? So if I make lambda sufficiently large, at some moment in time you will see an infinite component. Well, there is a little catch here, because we do need that not all weights are equal to 0, because otherwise you have nothing. You can also not have an infinite component. Okay? So this is the same as saying that in usual bond percolation on ZD, PC is strictly smaller than 1. Which is true in any dimension greater than or equal to 2. This is the equivalent of that. Okay. And the next question is, when is lambda c actually strictly positive? Theorem 4, positivity. And the theorem says that lambda c is positive when the gamma, which was alpha over d times tau minus 1, is strictly larger than 2. So gamma larger than 1 means that you have finite mean. Gamma larger than 2 means that you have finite variance.
Would you be able to raise the percolation board, please? Thank you.
Okay. All right. And the next theorem says that this is also a necessary condition. So lambda c is equal to 0 when gamma is in between 1 and 2. I'm not bothered about the case lambda is, gamma is equal to 2 here, but so this is a feature that is well known in random graph theory. So if you're dealing with a random graph, for example, this inhomogeneous random graph, the Norris-Reiting model, in which the variance of the degrees is infinite, then you have what they call instantaneous percolation. It's sometimes also called robustness of the model. And it basically means that however small I make my edge probabilities, like this, the effect of these edge probabilities is so dramatic that for any lambda a little bit positive, you immediately have a giant component. Okay? So that's true here. But it's not true here. So somehow as the tails of the degrees become thinner, the effect of raising lambda becomes smaller. And here you really have to raise it a substantial amount before you will start seeing the giant component. Whereas here it immediately appears. That's a bit weird. This does not occur in long-range percolation. There is no model in long-range percolation where you have a zero critical value while at the same time having bounded degrees, or let's say bounded expected degrees. So of course it is possible that you have lambda c which is equal to 0, but then all the degrees will be instantaneously infinity. Okay? So this is a new phase for percolation. All right. So that's a bit of a proof of this. Proof. Theorem 4. I'll first make my life a little easier, and I'll assume that the weights actually have a second moment. It is possible that gamma is still larger than 2 even if the weights have infinite second moment, but this, you will see that this simplifies the analysis a little bit, and then after that I can explain what changes when the second moment becomes infinite. All right. So what I'm using is that if I have percolation, there should be at least one path of length n starting from the origin. So let's call nn is the number of n step paths from 0. I might as well assume that they're self-avoiding. Then this is less than or equal to the probability that nn is greater than or equal to 1, and that's less than or equal to the expectation of nn. Okay? It seems an extremely crude bound, and it is. But I'm going to do something which is even worse, and that is that I will bound from above the edge probability by the exponent here. Which is always true. 1 minus e to the power minus x is bounded from above by x. Okay? All right. Okay, so then we continue with our bound. And that is less than or equal to, well, the edge probabilities. Of course, everything here is conditional on the w's. So you have to have a big sum here, x1 up to xn, and then a big expectation, which is now only over the w's. And then what do I have? Well, I have a lambda wx I minus 1, wxi, where the x's are the points in my path, and I divide that through by xi minus xi minus 1 raised to the power alpha. Okay? And of course I have to take a product. That's very important. All right. Now, the w's are independent. And of course what I see here is that I start with having a w0, wx1, and the next term contains the wx1, wx2, and the third term contains the wx2, wx3. So every w appears twice, except for the starting point and the end point. Right? So x0 appears once, but x1 appears twice. Once in the first H probability and once in the second. Now I'm assuming that the second moment is finite, so I can just take these expectations. First of all, I'm going to have a lambda to the power n, then I have a sum over x1 up to xn, and then I have a an expectation of w twice, and then I have an expectation of w squared for all the intermediate points, 1 up to n minus 1, and that's n minus 1 times. And then of course I still have these. The product over I is 1 up to n, 1 over x I minus 1 minus xi to the power alpha. Okay? So far so good. We change the boards because I'm almost there. So this is less than or equal. I have lambda to the power n, I have expectation of w squared to the power n minus 1, and then I have an expectation of w squared by Cauchy-Schwarz that's also smaller than the expectation of w squared inside. So I can bound this from above by lambda expectation of w squared to the power n, and then I still have to perform my sum. But bear in mind that we're now in the situation that alpha is larger than d, because if alpha was less than or equal to d, all my degrees were infinite almost surely, so that was not interesting. Then there was nothing to prove. So alpha is smaller than d, which makes this, when I sum it out over xi, finite. So I can basically perform my sum from xn, and then to xn minus 1, then to... So I get this sum, n times. And there we go. Okay, so what did we achieve? We achieved that the percolation probability is bounded from above by something to the power n. Now if that something is larger than 1, we're of course in problems, because then we could have achieved an easier bound without doing anything. But of course I still have my parameter lambda here. And what I'm trying to prove is that lambda needs to be a little positive in order for this probability to be positive. So if I take lambda such that this number here is strictly smaller than 1, then this will decay to 0 exponentially. So theta of lambda will be 0. So this converges to 0 if lambda is smaller than, well, 1 over this. Now that's a finite value. So not only do you prove that the percolation probability is 0 when lambda is smaller than this value, this also gives a bound on the critical value, which is actually this. So lambda c has to be larger than this. Okay. Now of course I was cheating a little because I was assuming here that the second moment is finite, but that's not always the case. Now if that is not the case, well, actually the nice thing is that we could regroup these variables and actually explicitly take the expectation. So what are we going to do when the second moment is not finite? Well, then the right hand side will always be infinite, so this is not a good bound. But of course we can adapt our bounds slightly and just say a minimum with 1 there. That's fine. That's of course always true. And, well, what happens then? Well, I get a minimum with 1 here. And that's a bit nastier because now I can no longer factorize all these equations. That's a bit of a pity. So you would think that it stops there. But, you know, you can again look at the structure of these paths, the structure of these expectations. And what you will see is that, for example, the W of x1 appears precisely twice. Once in the first term and once in the second term. So if I were able to somehow redistribute those in the correct way, then I might be able to create independence. The trick is to use Cauchy-Schwarz. So you have the first term, you have the second term, the third term, etc. In the first term of the Cauchy-Schwarz, you take all the odd terms, and in the other term for Cauchy-Schwarz, you get all the even terms. That means that every W is only there precisely once, and therefore the thing again factorizes. Okay, that's actually quite nice. So what do we get? Well, we get that this is less than or equal to the sum of x1 up to xn. Now I have to look at my notes, not to make a very foolish mistake. That's easy at this point. Right. Yeah. And then we get the product over I, the expectation of lambda wxi minus 1 wxi over xi minus 1 to the power alpha min 1 squared to the power n over 2. That's what it boils down to. Okay? So now we again have a power of n, but the expectation is a little bit more difficult. Okay? So, oh, no, that's not to the power n over 2, sorry, to the power 1/2. All right, so what do we do with this? Well, we can again put everything together.
Is the power half in the right place there?
I'm not entirely sure. Should it be gone?
Didn't the square brackets go around?
I should have n terms.
Shouldn't the square brackets that go around something bigger?
Well, this is what I have.
You just have something squared and then to the power half.
No, because the square is inside the expectation, whereas the half is outside.
It doesn't look like it from the way it's written.
Another set of brackets. There you go.
Better?
No.
We read this as the expectation of the square root. We're not reading it as the square root of the expectation, which is what you intend it to be read as.
Wait.
I don't know. I guess the appropriate number of brackets would resolve this problem. Okay. And actually, if you can compute this, you can bring the sum over x inside, and what you get is, now I'm reading it here, sum over x unequal to 0, the expectation, and I'm going to write a large bracket here to avoid confusion. Oh, W1 so the expectation of the square, and that to the power 1/2, and all of that raised to the power n. Okay, so again we get a power of n. So now the question is, can I make the thing that I'm raising to the power n sufficiently small by choosing lambda to be very small? Well, the downside is that actually this expectation is a bit more difficult. But it turns out to be an expectation that you can do. So if, this is the crucial estimate here, if the probability that W is larger than W is less than or equal to W to the power minus tau minus 1, then I'm writing G of U being the expectation of W1, W2 over U min 1 squared. That's going to be less than or equal to U to the power minus tau minus 1 times something relatively trivial, 1 plus the log of U. This is just a matter of doing the integration. Thanks. And if you stick that in, what you will see is that this sum is actually finite in the regime that I'm after here, this regime. So that's a small adaptation of the proof. Let me not go into the details, because I only have 5 minutes left. Let me say a few words about this. What is happening here? Well, the nice thing about this, about our model, is that we can do something like a block renormalization. So we're dealing with ZD. Now suppose I would chop up ZD in large blocks of a certain radius, which might depend on lambda. Then we know that the weights are all IID, and they're heavy-tailed. So I know precisely how the maximum value in a large block, how that grows. And that will grow like a power of the radius. Okay? Now if you do that appropriately, you will see that if you just take the maximum weight vertex in your block and use these to create a new ZD on a larger scale, and you only look at the connections between those vertices, it turns out that in this value you can make the connection probabilities to the nearest neighbors arbitrarily close to 1. As close to 1 as you like. Of course there's a bit of a problem, because this is not an independent percolation model. But it's a one-dependent percolation model. Actually a lot is known about one-dependent percolation problems. In particular, it's known that if the edge probabilities are sufficiently close to 1, then actually it will be supercritical, and therefore you will have an infinite component. So this shows that my special vertices of highest weights in large blocks will actually form an infinite component. Well, that means that there actually is an infinite component. So that's the proof. All right. Now, I promised a few more theorems, which I will not say anything about the proof. And this is all about the small world properties. So assume that we're in a setting where we're supercritical, so there's a giant component. Now, of course, we cannot say that the distances between two uniformly chosen vertices that grows, or identify how that grows, because we're in an infinite setting. But what we can do is investigate how the graph distance between two vertices that are very far apart grows, with the Euclidean distance between them. That's very similar to the graph distances between uniform points in a finite setting. Theorem 6. Fix lambda positive and gamma in between 1 and 2. We know that there is an infinite component because that's theorem 5. Then the distances in the infinite component between 0 and x is theta phi of log x. So if I take two vertices which are enormously far apart, then with high probability the number of edges that I need to take to connect the one to the other is only the log of the Euclidean distance between them. That's very small. So this corresponds to ultra small distances. This is when gamma is in between 1 and 2, and results like this are well known for random graphs without any geometry, and precisely in this regime where you have infinite variance degrees. Now this of course immediately raises the question, what happens if gamma is strictly larger than 2? So lambda larger than lambda c, gamma larger than 2, Well, then we actually don't know very much. But we do know that the limit of x tending to infinity of the probability that the distance along my cluster between 0 and x is greater than or equal to eta log x is 1 for some eta. So that means that the distances are at least logarithmic in the Euclidean distance between the two vertices in this other regime. We have some stronger results proving that in certain settings you actually get a positive power of the norm of x here, which is a lot larger, but our results are far from complete. But given the time, I stop here.
Maybe time for one or two short questions.
Do you know how many components you have when you have an infinite component?
Infinitely many.
Really?
Yes, I mean it's an ergodic system,
Oh.
and you have the positive probability of having a finite cluster. So there's going to be infinitely many finite clusters. I think there's only one case where you only have one component, and that's when the degree is infinite almost surely. Then you're only going to have one component. It's actually interesting to see what the diameter of that object is. It's probably finite. Oh, there's a unique infinite component. That was your question?
Yes.
Okay, I'm sorry. Misheard.
What can we say about number of loops in this model? Like triangles, density of triangles, and so on?
Well, every vertex is going to have a triangle with positive probability. And I mean, it's a stationary ergodic system, so the expected number of triangles per vertex is probably finite and positive. That would be my guess. But we haven't analyzed that in any detail.
I mean, most of those like random graph, let's say models,
Yes.
they locally tree-like basically.
Yeah, this one is not. Because, I mean, you have a bounded away from zero probability of being connected to your neighbor, to another neighbor, and that they're connected to one another. So this really has positive clustering. Yes.
Okay, so let's thank Remco again and convener.